Good morning, all of you. Welcome back to the online sessions on signals and systems. So, in this today's class, what we do is before we go to the third unit called Laplace transforms, I just wanted to have a recap of the various topics which we have covered until today. Right. So, in the earlier video, we have seen the basics of signals and systems. Now, I will be covering up. I will be covering about the topics which we have dealt in the first two units. Okay. So, a signal is a real valued function of one or more real variables. So, voltage across. Now, how can we define a signal? A signal is nothing but any real valued any real valued function of one or more variables is known as a signal for us. Or a signal can be defined as a physical quantity which varies based on one or more variables is also called as a signal for us. So signal can be defined in multiple ways. The meaning of signal is going to be somewhat differently interpreted by different people. See, for example, if an electrical engineer is there, for him, the voltage across a resistor is known as a signal. And for him, the current through a resistor is also known as a signal. When you go to the stock exchange, the price of the Google stock at the end of each trading day is known as a signal for him. So similarly, the amount of rain at certain time period as a function of latitude and longitude is a signal for the weather forecasting engineer. Atmospheric pressure as a function of location and time is a signal for the atmospheric engineer. So like that, the signal is normally going to be represented in many forms. So signal can be represented in many ways. Now in the signals and systems part exactly to speak about the definition for signal, we can write as a signal is a real valued function of one or more real variables. Now the signal is a real or a complex valued function. Both are valid in the signals and systems. So hence I can say that a signal is a real valued function or a complex valued function of one or more real variables is known as a signal. That means signal can be represented as a function basically. So a function, say for example, g of t is known as a function. So this function I can write as g is the name of a function and t is a independent variable. Now we can have g of t1 comma t2 comma t3 comma so on up to tn inside this particular parenthesis. Right, inside this braces we can have like that. So therefore I can write a g of t as a signal, or I can say it as a function for us. So the physical signals have certain units. Say for example, if you are dealing with a voltage signal, it is going to have a units called volts. If it is a current signal, it is going to have units called amperes. If it is a power signal, it is going to have the units such as watts. Right. So similar to that, based on the applications, we normally going to have the signal units. Okay. Now signals can be measured. Usually signals can be measured. So that means signal is normally measured and people are going to give a value to a signal. Say 2 volts, 10 volts, 15 volts in case of a voltage. In case of current, 0.5 amperes, 1 ampere, 2 amperes, 3 amperes, whenever a signal is going to be in terms of the current. So like that, a signals can be measured with some giving some values. Now mathematically, how we represent a signal? We represent signal as g of t. So g of t may tend to g of the value of t, if it is taken as 0, value of t is taken as o, sorry, value of t is taken as 0, then I can say g of 0. That means the value of the function at a time period t is equal to 0. What is that particular value? Now if you want to represent signal in terms of area, total area of a signal, you have to find out. Signal is going to vary always between the limits. Say some minus t to plus t, minus t1 to plus t2, minus t to plus infinity. So minus infinity is nothing but any arbitrary value is going to be called as infinity for us. So you can represent signal in terms of the entire area with limits. Then we can use a symbol called integration. And a signal can be energy signal. If at all you wanted to find out energy of a signal, what we do? Simply we find out the scale, the integration value of square of the absolute value is known as a energy for us. So like this, the mathematical form for a measurement is basically a functional measurement. So functionally, we normally going to find out the value for the signal. Similarly, we discussed about a system. What is basically a system? A system is always going to take some signals as the input and produces some output in terms of the signals. So therefore, a system takes signals as inputs and produces signals as the outputs, where this g of t is the input signal, f of t is as output signal, and the system is normally going to process g of t to produce the output signal f of t. Now here, uh, what the functionality the system is normally going to provide? System may provide any functionality, like say differentiation, integration, or some other complex operations the system may perform really. So in that scenario, if the system is performing differentiation, what the mathematical form of that particular system now? F of t can write as equal to my d by dt of g of t. That means the system is performing differentiation. Similar system may perform integration. In that case, I can write integral of some limits t minus 1 to t gu of du is nothing but a system representation. So like that, let us suppose a system is doing some complex operations. So in that case, we normally going to represent the system as g of t into e power minus some 2 pi I s of t dt or e power minus j omega naught t. So any representation we can do in terms of the complex notations. If at all we have a complex signal, we always represent by using e power minus j omega t, e power plus j omega t. This j is going to be the complex signal representation for us. So what are the practical physical systems which we normally encounter? We normally encounter practical systems are going to be electrical systems, electronic systems. All these are the physical systems we are seeing every day. So that means here these systems are going to, this electrical system is there, for example. What the electrical system input is going to be? Voltage is going to be the input to the electrical system, and voltage may be the output and current may be the output of a electrical system. If the system is, say for example, building, say building is a system. Now what is the input to the building? Earth shaking input is going to, earth shaking in is going to be the input to the signal. Then building shaking is going to be the output signal. So like that, the signal, if a building is taken as the signal. The next type of system is going to be, say for example, an audio amplifier. So the input of the signal is going to be a very small signal, output of signal is going to be very large signal. So that is going to be the audio amplifier input and output system. So these are all the practical systems which we are going to encounter in the practical world. And signal, we have another variety, we don't have in the syllabus energy and power, but still they are going to be very primitive and very basic representations of a signal. So energy of a signal, that means energy of a signal can be represented something like, if I have a voltage signal. Now what is the energy of that voltage signal? I want to find out. So what I'll do now, I simply say integral of v square dt, v square dt. Now, if V is going to be dependent on time, then I'll write V of t square dt. So I'll find out modulus value. If at all any complex components are going to be there inside this function, this complex components are simply converted into a real value. And that real value square, we are doing it. Then we are integrating that entire function over the limits until the where the signal is normally going to get provided. So all that things we normally going to consider to find out energy of the signal. So the mathematical representation for the energy of a signal is going to be simply integration of the square of absolute value of that particular signal is known as the representation of the energy of the signal for us. So the practical example, say, of an energy signal is going to be the pulse signal. What is a pulse? Pulse is normally going to be just, it's going to have one step and one step up and one step down. So after stepping up, it is going to come down after some instance of time period. After that, the signal is not going to exist. That means, see here, if we take the limits, if we take the entire limits, now what I can have now, how I can represent a system as this g of t square represented over the limits minus infinity to minus t plus t to infinity, means what? The entire signal is represented extending between the entire range under consideration as minus infinity to plus infinity. So when you consider that for a limit of t tends to infinity, the value should be equal to 0. That means the energy signals are going to really end up at some instance of time period. They are not going to exist for the entire duration of the time period. Is simply known as the energy signal. Something like energy of a human being. So until how long your energy is going to get there inside human being? Until you sleep, energy is there. Once your energy is totally lost, then what will happen? You simply go to sleep. We all go to sleep. Then we once again regain the energy. With that energy, we normally going to perform our duties. Similar to that is going to be the energy for a signal for us now. So we normally going to have a two types of signals, something like pulse signal and exponentially decaying signals. So when it is going to be exponentially decaying signal, the signal is decaying continuously. Means what? Exponentially signal is decaying exponentially down. So how the form of the signal is going to be? It is simply decreasing exponentially. That is called a decaying signal for us. So that means decaying signal is going to come to zero at a particular instance of time. After that, we are not going to have any value of the signal. So for such signal, we can able to find out the energy. So therefore, that type of signals are known as the energy signals. That means energy signals are always going to come up with a finite duration, and that energy signal is also going to be a bounded signal. That means it is normally going to happen over a particular limits and over a particular duration. The signal value is going to be there. Other than that, the signal value is not going to be there. So such signal is known as the signal, and hence we can find out the energy of signal, something like this. Now similar, if we find out average value of this particular energy signal, we normally going to get the power signal. So this is the energy signal integration of g of t whole square dt is energy signal. And if you find out average value, what is t? T is going to be the time period of the signal under consideration. So if you find out 1 by t means what? You're finding out mean value of this particular entire signal in terms of energy. If you find out mean value of that, we normally going to find out the power which is there inside this particular signal. So therefore the power signal can be represented something like this for us. Okay. And next come to the units of power. What is the power unit? It is going to be watts. We already know the units of power is always going to be in terms of watts, right? What is p? P is equal to I into, sorry, p is equal to v into I. So the units are going to be watts. Now P is equal to what I can write as? I can write P is equal to I square R V square by R. Two equations we can write. So P is equal to V into I. V can be written in terms of I as V is equal to IR. Basic formula for V is equal to what? Voltage drop is equal to I into R. So I when I write in the equation for power, P is equal to I into R for V, then I can have I square R. Similarly, I can have V square by R for the power relationship. Now we're replacing this V by G of t because it is dependent on the time period t. So we're representing a signal which depends on some independent parameter t. Therefore, we're writing as some G of t as a function. So therefore, I am writing something like G of t square by R. This is the representation of the power of a signal. Now, usually we do not care about the load resistance. Therefore, we normalize it to 1 for the simplification purpose. Okay. Now, in many applications, the effect of signal varies as a logarithmic scale of the signal. So, usually we consider practically logarithmic scale as the scale of the signal to be measured. So, signal is normally measured in a logarithmic scale rather than in other scales. So therefore, logarithmic scale is going to be more popular. So the logarithmic scale means what? Decibel scale. So dB scale is usually logarithmic in nature. Therefore, we are normally going to have a logarithmic scale. Now, what is the benefit of logarithmic scale? The benefit of logarithmic scale is that if the value is too small, even then we can represent that value reasonably. Practically, we can show that value with a reasonable parameters. So if the signal value is very small in terms of milliwatts or less than milliwatts, we can represent them by using a dBm scale. So dBW scale we can represent. If the signal value is going to be more than 1 watt, then we can represent by using dBW type of the scale. So if at all we represent power in decibels, then what we can do now, we simply perform 10 log of that particular value of the signal. So that means this bell unit is normally used is for two large values and two small values of the power signals. Then we discussed about various classifications of signals. So different classifications means what we have seen about the continuous time signal, discrete time signal. So under continuous time signal, we normally going to have deterministic, non-deterministic signals. We're going to have periodic, non-periodic signals. Same thing is going to be true. Whatever is going to be true for continuous time signal, same thing is going to be true for the discrete time signal also. So that means discrete time signal can also be deterministic, non-deterministic. Discrete time signal can also be periodic, non-periodic. So two important things are there for system signal classifications. One is going to be periodic signal, non-periodic signal, deterministic signal, and a non-deterministic signal. So these four are the basic classifications of the signals which we have in the syllabus. And we discussed about what is deterministic, what is non-deterministic. We discussed about what is random and non-deterministic signal, what is periodic, and what is the aperiodic signal nature for us. And if you really go further in deterministic signals also, we'll find many types of the varieties. See, we can have a deterministic signal for continuous time signal. We can have it for a discrete time signal, sorry. We can have it for a discrete time signals, right? So now thereby we can just have it a continuous time, continuous valid signal, continuous time, discrete valid signal, discrete time, continuous, all possibilities we normally going to get. Discrete time, discrete valued signals. So that means 2 power 2, 4 combinations we normally going to get. We have a continuous time signal, we have discrete time signal. So 2 power 2 is going to be 4. Therefore we're going to have 4 combinations of the signals can be formed by using these two type of the signals which we have. So all these four combinations, sorry, all these four combinations will be coming under the discrete time. All these four combinations can come under the deterministic type of the signals. Okay, so these two are the varieties these four are the varieties which we have seen, that deterministic, non-deterministic, periodic, and aperiodic type of the signals as the classifications we have under continuous time signal and discrete time signals. Okay, so under continuous time signal, we're going to have periodic, aperiodic signals, deterministic, non-deterministic signals. Under discrete time signals also, we're going to have both deterministic, non-deterministic, periodic, and aperiodic signals. All this we discussed. So these are the various signal representations which we can have it over here. So this signal is simply increasing, if you see carefully, exponentially. If it is coming down, it is simply decreasing exponentially. In the reverse order, if you draw this, the signal can be represented as something like decreasing exponentially. It is increasing, say, exponentially. Now this is known as a continuous time signal, because continuous signal is varying. Now this is nothing but a discrete time signal. Discrete time signal, it is going to be discrete time, discrete valid signal. This is nothing but discrete time, continuous valid signal. This is going to be the third one, that is going to be like discrete time, continuous valid type of the signal. So these are the various signals we can have, and some of the operations which you can perform, as we discussed, like we can shift the we can shift the signal towards right and towards left. So imagine if this is a signal we have, this signal is starting at this time period t, for example. So if we are shifting this signal towards right, then how I can represent that signal as? I can represent mathematical that signal as g of t minus t, because the signal has been shifted by t. What does it mean by this? The resultant signal is coming after this signal delayed by time period t. Therefore, it is delayed by time period t. So therefore, I can write this as delayed signal. Similarly, time advanced signal. What does it mean by, if you shift this time signal towards left? Now, with respect to this reference signal, how is the signal? The signal is coming before this signal by a time period t. Therefore, I can write this as g of t plus t. It is a time advanced type of the signal for us. Similarly, we can have other operations like time scaling operation. In time scaling, you can shrink the signal, you can expand the signal. In figure B, you can see you are shrinking the signal by 2. In the next one, you can simply expand a signal by 2. If you are shrinking the signal by 2, you represent as g of 2t. If you are expanding signal, you can represent it by g of t by 2. So this is what the expanded signal, compressed signal. Similarly, time reversal. Imagine this is the reference signal for us. We are reversing the signal in the time axis. So g of minus t we are doing. So amplitude we are not reversing, only time we are reversing. Therefore, time is what? X-axis is the time period. See, t is on the x-axis. Y is going to be the amplitude. So on the time axis, we normally going to shift. We are normally going to have the time reversal property. See this now on the time here on the reference signal figure A, we have plus 5, we'll be having minus 5. Now similarly this side we have exponentially, this is exponentially decaying signal now. This exponential decaying signal on the time axis is minus 2. After time reversal it will be plus 2. Then on y-axis we are not changing. Then we are simply joining that. Those two curves. This is the curve nature. This is going to be linear nature. Similarly, I have another signal here if you see carefully. This is minus 1. The signal is extending between minus 1 to minus 5. Minus 1 to minus 5. Now this signal representation is in e power plus t by 2. Now the same signal is time reversed. When it is time reversed, this minus 1 becomes plus 1, minus 5 becomes plus 5. And rest of the things remains going to be same for us. So this is the time reversal type of the signal. So each of these operations correspond to a linear systems. So in a linear system, what happens? The form of the signal is normally not going to change. The next variety you normally going to have is the impulse signal. We have seen impulse signal value. The value of the area of the impulse signal is always going to be 1. So that is known as the impulse signal. Finding out integration of signal is known as what? Finding out area of the signal. So if the area of the signal is equal to 1, that signal is simply known as the impulse signal for us. Impulse signal is represented by using delta of t, which you already know. The next one is going to be the properties of the unit impulse signal. Impulse signal is going to exhibit certain properties. What are the properties of it? It exhibits a sampling property, it exhibits convolution property, it exhibits multiplication property. Okay, all these properties is going to exhibit, and one more is going to be Fourier transform. So Fourier transform is actually not mentioned here, but anyway we discuss for Laplace transforms as far as theory is concerned. So Fourier transform unit impulse is constant 1 for all the frequencies. So if you find out Fourier transform of a unit impulse function, the value of that will be equal to 1 for all the frequencies. So this also we discuss in the coming classes. When we discuss about the Laplace transforms, we have to just touch about the Fourier transform. By touching it, we normally go to the Laplace transforms. Okay. Well, so these are the various properties of the unit impulse signal we have seen. And next one is a unit step. What is a step signal? You normally going to have a single step. What is a single step? At time t is equal to 0, the value of signal is going to maximum. That means one step, it is going to take one step. What is a pulse signal? After some time period, you're going to have one more step down. The duration, that means this duration only the pulse is going to exist. That signal is known as a pulse signal for us. So pulse signal is always going to be a finite duration signal is known as a pulse signal for us, whereas infinite duration is going to be known as a unit step signal. It's going to be heaviside signal. But only thing is in unit step signal, the signal value is going to be 1 for all time period t less than 0. This is the time axis, x-axis. So for infinite time period after t is equal to 0, the value of signal is equal to 1, just like a DC line. Before 0, t is equal to 0, the value is equal to 1. That is known as a unit step type of the signal for us. Okay. Now the integration of unit impulse signal is nothing but equal to unit step signal. Okay. The next one is going to be sync function. That is also special function for us. So we have just representation of this particular function. So sync, SINC of t. I can represent this as sine. If it is represented with pi, we can have sine pi t by pi t. So if this is pi is equal to 1, then I'm going to have 1 over here. I can write this as sine t by t. Remember? Now, what is the form of this particular function? When you draw this function, how it looks like now this function looks like this. This sinc function looks like this. When you substitute all the values of t, the function is normally going to give us a shape of the function, something like this. All right. Right. So now this is what the function we're normally going to get, and we're normally going to get asymptotically changing function. What is the meaning of asymptotically changing? The value of the function one it will be more close to zero at t as t tends to infinity, but it never touches to zero. That is called asymptotically varying type of the signal. Then next we have seen the periodic signal. What is the periodic signal? The periodic signal is normally going to get repeats itself in time period for all time t greater than 0. For all time t greater than 0. That is called a periodic signal. So the periodic signal of say a tan signal, tan function is there. The tan function is going to be periodic after every pi interval. Sine function is going to be periodic after every 2 pi interval. Similarly, cos function is periodic for every 2 pi interval. That means for every 2 pi interval, the sine function, cos functions are going to repeat itself. For every pi interval, the tan function is also going to repeat itself. And hence, they are simply known as the periodic type of the signals. The next one, Fourier series, Fourier transforms is not there in the syllabus. But anyway, we have to just have a touch of this. Fourier series is normally going to give us some information about the signal representation. So we can say by seeing this particular Fourier series representation, every signal is normally going to have various components. What are the components the signal is going to have? The signal is going to have a DC component. The signal is going to have a cosine component. The signal is going to have basically sine component. And these components are normally going to come up with the exponential part as well. So they're going to have they can be exponential functions of cos, exponential functions of sine as well. So all these are the components which are normally going to exist inside the signal. Whereas the signal coefficients are normally equal to an and bn. So an is going to be the signal coefficient in the of the cos function. Bn is going to be signal coefficient of the sine function. So inside signal we have discussed that is going to have a cos component, you're going to have sine components. So the coefficient of cos component is going to be an, coefficient of sine component is going to be equal to bn of this particular signal. So inside this g of t we normally going to have many such components of the signal. So first one is going to be DC component, no frequency variations. Second function is going to be the AC component, cos of omega nt, sine of omega nt. What is omega? 2 pi by t naught. So this omega is nothing but the frequency component. Omega is nothing but the frequency component. Means what? The signal is going to have frequency variations. That is what the signal representation that we normally going to have. And this can further be expanded to represent this in terms of the time domain and the facial domain. So normally what is basically a signal, say if you write g of t by not considering all these things, what we can have simply g of t is equal to an cos of omega t plus theta. So this omega t n 2 pi f naught is nothing but omega naught this is t plus theta. So a function is normally going to have an amplitude as say for example a cos function represented here. A cos function is normally going to have an amplitude, it's going to have a time period t, and it's going to have a angular displacement theta. So these three are the basic parameters of the function, or a basic parameters of the signal, that is frequency or time period, whatever it is, frequency or time period, theta, and the amplitude, or the basic parameters of this particular signal. Okay, so after this we discussed about various systems such as casual system, non-casual system, stable system, non-stable, unstable system, linear system, non-linear system, time variant system, time invariant system, and shift invariant system also we have seen. So all these systems we have seen with some representations in the previous classes, and we encountered one operation performed by the system on the signals. What basically system is going to do? System is normally going to perform some implementation on the signals. As a result, we get some predefined result. One of the performance is going to be the convolution. So basically the h of t is known as the system characteristics. V of t, for example, this is the input signal. So this input signal is normally going to get changed based on the implementation of the system. So that means that is normally going to get explained by convolution process. So this basic convolution process is known as impulse response of the system. That means this h of t is basically equal to the response of the system to the impulse signal. When the input of the system is an impulse signal, it is going to give us a response in terms of h of t, which is nothing but characteristic of the signal. Then characteristics of the system. When such a impulse response system is used, then it is going to be called as impulse response system for us. So usually for practical applications, we always compare the response of our system with respect to the impulse response. So therefore, we consider the impulse response here. So which is nothing but convolution of the two things. What are the two things? Convolution of the signal characteristics and the system characteristics. Thereby we normally going to get the response. So the same convolution, when you convert this into frequency domain, it will be converted like a multiplication. So this is time domain representation of multiplication. This is going to be the frequency domain. Now what do you mean by time domain and frequency domain? If a signal is represented with respect to time, it is called time domain. If a signal is represented with respect to frequency f, it is known as the frequency domain representation. See in this equation, all these are represented with the time domain t. That means omega of t, h of t, v of t. All these are time domain representation. Similarly, w of f, h of f, v of f. All these are frequency domain representations of the signals. So these two are the functions which we have performed in the last classes. And finally, we have two more last system representations. One is going to be a system can be represented in terms of differential equation, and a system can be represented in terms of difference equation. So a differential equation means what? There should be some differential part existed inside the equation. That means d by dt of y of t is nothing but what? Differentiation of y of t. For the nth order system, if you represent order of the system is going to be n, then we normally going to have for the nth order system. So if the order of the system is going to be n, then we normally going to have how many differentiations? We normally going to get two differentiations. That is, we normally go with 0 up to 2. 0 0 and 1, 2 are there. That means two representations we normally going to have for second order system. Third order system, we normally going to get three components. Fourth order system, we normally going to get four components. So these are all the system representations for the order, based on the order. So now this is the representation of a system with respect to differential equation. That means if you represent with respect to differential equation, it simply becomes like a differential equation form of the system representation. So whenever we represent any system, what is so important is that there should be an output signal, there should be an input signal, and it should be guided by equal to symbol. Okay, some representation of equality has to be there for a system to represent. So therefore, system means what? System is going to have some functionality. Say d by dt is nothing but functionality of the system or implementation of the system. It's going to have the input, okay, and it is going to give you the output. Similarly, you normally going to have the difference equation. What is difference equation? Y of n minus k is nothing but the difference equation. So this is what the difference equation we normally going to have for nth order system. So like this, we normally represent systems by two representations. Like that means when you write a system equation, we're going to write a system equation in either one of these forms. One is going to be differential equation form, difference equation form, and we have a basic equations called as linear constant coefficient differential equation and linear constant coefficient difference equation. So they are not exponent, they are not changing exponentially. If the exponential changes, the e power j omega should come into picture. That is not coming here. We don't have that complex systems. So we have a linear coefficient differential equation in the syllabus. So these two are the representations of the differential equation and the difference equations. So thank you very much. With this, we end up with this particular session, and tomorrow session we start up with the introduction to the Laplace transform. We'll have a brief discussion about what is Fourier transform, why we are simply going to the Laplace transforms. Thank you very much for today's